This sumobot is meant to push another sumobot out of a circular platform, and in order to do this it needs a way to detect the other sumobot. And for this I have 5 range sensors, 3 in the front and 1 on either side. And in this video I'm going to write the code necessary to take the input from these sensors and convert that to a corresponding enemy position. And this video is going to be structured in the same way as the last video where I worked with the line sensors, in that I'm going to structure the code in different layers. So here is the software architecture, and at the bottom I have I'm going to implement an I2C driver, because that's the interface that these sensors have. And then once I have that working, I'm going to implement a driver for the actual sensor. But I'm not going to implement that driver in this video because these sensors are actually quite complicated. They even have a microcontroller on them, and it requires quite a bunch of code to get this driver working. And I already have this driver ready, and I've written a long blog post about how it works. So I'm going to link that blog post in the description, and so if you're interested you can read that. And in this video I'm simply just going to move the code into the project. But then I'm also going to implement a third software layer called enemy, which is going to translate the individual range measurements into discrete enemy positions. And this is just here to give a nicer interface for the rest of the application code, which I'm going to write later. And this is similar to what I did for the line sensors. So let's get started with the I2C driver. So first I begin by creating a new local Git branch and call that feature enemy detection. And then I'm going to create the 2 files for the I2C driver. So that's just going to be an implementation file and a header file. And then I can add that to my make file immediately. And moving into the header file, I can begin by creating the interface to the I2C driver. So first I will have a function to initialize the driver, and then I will have 2 functions to transmit data over the I2C lines. So I need 1 function to write data to the sensors and 1 function to read data from the sensors. So one is going to be called I2C write, and basically what I'm going to be using the I2C driver for in this project is going to be to write and read from the registers of the range sensors. So this function is going to take the address to this register as well as the data I want to write to the register. And this address can be of different size. In this case it's going to be either 8 bits or 16 bits, but to make the interface a bit more general, I'm going to pass it as a byte array and then also pass the size of this byte array. And this is going to allow me to use this function to send addresses of different sizes, and then do the same for the data. And this function is going to return an error code, which is just going to be an enum to give some more information about the error that happened. And then a corresponding function for read, which is going to look very similar. It's going to take the address, the size of the address, and then it's going to take a pointer to the data that is received. So this can't be const, since I'm going to write to this pointer inside this function, and then also the size. So this value here is going to be the data that is read from with this function. Then I'm also going to have a bunch of wrapper functions to make the interface a bit nicer. And these are just going to wrap these other functions here, and that's just going to make the calling code a bit nicer, because I'm not going to have to pass 4 arguments each time, because most of the time I will just be reading 8-bit registers or 16-bit registers. And then I'll include here, and also a small comment. And this I2C driver, I'm just going to make this polling based, so I will just be polling and I won't use any interrupts, because for this application or in this project I'm not going to be able to do anything useful while the transmission is happening, so there's really not any point for me to complicate things with interrupts here. So this driver is actually going to be quite simple. So that's it for the header file. Let's now move on to the implementation file. Or well, there's one more function I need inside this header file, and that is a function to set the address of the slave that I'm writing to. Because in this setup, where I have my microcontroller connected to the range sensors, the microcontroller is going to act as the master, and the range sensors are going to act as slaves. And since I have multiple sensors, it means that I need to change the address when I want to write to another sensor. Also say that this is just a driver for an I2C master. So then beginning with the initialization function. The first thing I will do in this function is to make sure that the IO pins that are going to be used for the I2C lines are correctly configured. And they should be, because I configure all of the IO pins inside the IO driver, which I showed in a previous video. So here I'm just going to assert that the configuration is correct. And for I2C, we only use 2 pins, one for clock and one for data. And this is the configuration I expect it to have. It should be selected for alternative 3 to be MUX to the I2C peripheral. And then I can get the current configuration for both pins and assert that the configuration is correct, like that. We can just have a quick look inside the IO driver as well. So here is where they are configured. And once we have checked that, I can move on to actually initialize the I2C peripheral. And as usual, to know how to initialize or configure the peripherals of a microcontroller, you have to look inside the datasheet. And the I2C peripheral is well explained inside the datasheet of my microcontroller, the MSB430. I'm not going to refer to it in this video, and instead just show you the register writes immediately. So first of all, I have to write to a control register and put the I2C peripheral in reset, because it has to be in reset while you write the configuration. Of course, exactly how an I2C peripheral is configured is going to vary depending on the microcontroller, but regardless of the microcontroller, you will have to write to a bunch of registers. And I also think it's a good idea to just write some short comments explaining each register write. And then I write to another control register to configure the peripheral for single master, synchronous mode, and I2C mode. And this means that it's only a single master, because the I2C protocol also supports multi-master mode. But in my case, it's just going to be a single master, the microcontroller. And then I need enable synchronous mode, because the communication is going to be synced with a clock signal. And finally, I set the I2C mode, and this has to be set because this particular peripheral or module hardware block can also be used for other protocols. And next I need to select the source I'm going to use as a clock, and similar to all of the other peripherals, I will be using the submaster clock. And then I have to write to this register. But this clock source runs much faster than I can use for I2C, which means that I have to divide it down with a clock divider. And then I write to these 2 registers, which is going to divide the clock down by 160, which is going to be an I2C clock speed of around 100,000 Hertz, which is a reasonable clock speed for this application. And this is actually all there is for the configuration in my case. So now I'm going to put it out of reset again, which means I have to clear the reset bit. And finally, I'm also going to set a default slave address. And for convenience, I'm just going to use the same default address as the range sensor has. So let's then also add a function for writing the slave address. And that's just going to be a write to this register. So now we can move on to the functions for writing and reading data over the I2C interface. But first, let me just add these, all of these functions as empty functions to make sure that the code builds. And these functions are just going to call the other functions. So this is going to be I2C read. And that's going to take a pointer to this address. And it's going to be 1 byte size, since it only takes 1 byte. And same with the data. and this one is going to be like this, and then it's going to be a point, cast this to an 8-bit pointer, and that's going to be 2. This is going to I2C read address 1, data, and then 4, since it's a 32-bit data value, and finally I2C write address 1, data 1. So let's see if this builds now. It does not. Oh yeah, I need to add some dummy return value here as well. And also include the microcontroller header file. Yes, and also fix the mapping up here. So one problem I noticed here is that for the I2C peripheral, the only pins that can be assigned to I2C are the pin 6 and pin 7 of port 1. And in a previous video, I accidentally used pin 6 for the PWM signal for the left motor. So I'm going to have to change this now so that I can use I2C. So I'm going to move that to 26 instead, because the timer peripheral can also be assigned to port 2 pin 6. And I can also remove the configuration for 5 and 12. Now let's see if this builds. Yeah, good. So coming back to the I2C driver, let's begin by implementing the function for writing data to a particular address. But the first thing I will do in this function is to assert or do some sanity checking that I have given a valid address and valid sizes. Just copy paste this to the other function as well. And then I'm going to create a separate function for handling the start of a transmission, and I will call this I2C start TX transfer, and this is going to take the address and the address size. So this function is basically going to send the address to get the transmission started, and if this function returns an error, I will return immediately here. So let's also implement this function. It's going to be a static function, and this in turn I'm also going to use a separate function called I2C send address. And the reason I'm adding these extra functions here is because there is going to be some duplicated code between the I2C write and the I2C read, so I just want to reduce the overall code duplication. And I think it also makes the code a bit more readable to have these functions here. So the first thing I will do when I'm going to start a transmission where the master is going to be sending the data is going to be to configure the I2C peripheral as a sender. And to do this, I have to write to this control register here. And in I2C, each communication or each transfer begins with a start condition and ends with a stop condition. So what I'm going to do next is to send the start condition. So I will have function called I2C send start condition. And I'm making this a static inline function, since it's just going to be a one-liner writing to a single register. One thing with the MSP430 is that when you write the start condition, it also sends the slave address, so it's not just the start condition. So I can just add this to my comment. And then once I've sent the start condition, I should wait for the start condition to actually be sent before sending any bytes, or that's how it usually is. But on the MSP430, you also have to write the first byte you're going to send before waiting for the start condition to be sent. So here I'm going to write the first byte. So that's going to be the first byte of the address, which I'm also going to have a separate function for. And I'm adding a comment here as well. And once I have transmitted or set the first byte, then I can wait for the start condition. And for all of these functions, as soon as I see an error anywhere, I'm going to return from the function immediately. And sending a byte is just a simple matter of writing to a single 8-bit register. So this is also going to be an inline function like this. And then for the function to wait for the start condition, here I'm going to have a while loop, but with a timeout. Well, let's just start with the while loop first. So I need to wait until this bit in the register has been cleared, because then I know that the start condition has been sent. And then I can also check if there is any error here by checking the status register. Or I can check here if I got a NAC from the, or a non-acknowledgement from the slave. And in that case, I can report an error, and otherwise everything was okay. And then as for the timeout, I mean, in case this never becomes clear, I don't want to be stuck here endlessly. Instead, I want to return another error. So I'm going to have a retry count. And for each iteration, I'm going to decrement this retry count, or this retries variable. And if retries is 0 here, then I turn I2C result error timeout, like that. And once I waited for the start condition, I can then wait the byte to be transmitted. So I'm going to have a wait function for that as well. And this is going to look similar to the other function, but here I'm going to check another bit, basically the interrupt bit that is set when a byte has been transmitted. And here I'm going to do the same to check if I got the NAC again. And also similar to the other function, I'm going to have a timeout. And if retry is 0, I'm going to return timeout, like that. Okay. So if it's just a single byte, I'm actually done at this point. But if the address is several bytes, I also need to send the rest of the bytes. And that's what I'm going to do now inside a while loop, or inside a for loop. So I'm going to start this from 1, since I've already sent the first byte, and go up to the address size. And here is just a matter of setting each byte and then waiting for each byte to be sent. And if there is ever an error, I return immediately. And then finally return the result. So that's it for the send address function. And continuing on with the write function. At this point, after start TX transfer has returned, it means that I've sent the start condition, and I've sent the slave address, and I've also sent the address to the register, or to the memory location I'm writing to. So the next thing I need to do is to send the data. And this is just going to be a for loop. And I'm going to make this a 16-bit index variable here, because technically this could be larger than 256. It's not going to be in my application, but why not? Data size. And this is going to be similar to the other function, where I sent the rest of the address bytes. So first I set TX byte that I'm going to send, and then I wait for it to be sent, and if I get an error, I return it. And when I send data like this, it's going to end up being sent from the... I mean, if there is a value that is multiple bytes, there are two ways, there are two orders you can send the data in. Either you start from the most significant byte or from the least significant byte. And the range sensor expects the data to be sent from most to least significant. So that's what I'm doing in this driver. So I'm going to add a comment about that. Can also add that here. And I will also comment about that inside my header file. So it's clear. And that's all there is to the write function. So let's see if this builds now. Yes, I have to define this as well. And since it's a 16-bit integer, I'm just going to use the max value for this, for a 16-bit integer, to make this delay as long as I can. Like that. Yeah, good. So moving on to the read function. And then, so the first thing I will do in the read function is going to be to start an RX transmission or a read transmission. So similar to the write function, I'm going to have a function to start a read transmission. There should be a result here. So the function for I2C result, I2C start RX transfer. But compared to the TX transfer function, I'm not only going to send the address here, I also need to reconfigure the I2C peripheral to act as a receiver. But first I will send the address. Then I need to configure as receiver. Because when I read from the slave, I'm expecting to receive bytes from the slave or from the sensor, in this case. So then the peripheral needs to be in receiver mode. So I need to clear this bit, and then I need to send a start condition to start the RX transmission. And I also need to wait for the start condition to be sent. And once that's done, then I'm ready to begin receiving bytes. And when it comes to reading, I'm also going to get the bytes in a byte order from most to least significant byte. It's going to be a for loop. And when I receive the bytes, or in this for loop, I will have to iterate in the opposite order, going from the last byte to the least significant byte. So here I'm going to have a similar function for receiving a byte. So wait RX byte, and if there is an error I will return. And then I'm going to, once the byte has been received, I'm going to set the byte inside the data array that I will return from this function. So let's implement these two functions as well. I think I'm gonna move this up instead, so they are next to each other. Static, wait X byte, and here I'm also going to have a while loop checking a specific bit, or in this case it's going to be the RX interrupt. So I might as well actually copy the content of this function and just paste it in here, because it's very similar. The only difference is the bit I'm checking. And oh, this error returner is wrong. This should be RX and this should be TX. Like this. And then I will have a function, an inline function, to retrieve the received byte. And for that I need to read from the receive buffer like this. Then I can continue with the read function. And note, in this for loop, I'm receiving all bytes except for the last byte, because the way the peripheral on the MSP430 expects this to work is that I have to send a stop condition before I wait for the last byte. So here I'm going to have a function to stop the I2C transfer. I can just explain what I'm doing here. I'll stop before last byte. And this is a detail that can trip you up if you don't read the datasheet carefully. It took some time for me to realize that this was necessary. Oh yeah, I should also stop the transfer inside the write function, of course. So I should have a call to stop transfer here. Because, as I said before, each complete I2C transfer begins with a start condition and ends with a stop condition. So what this stop transfer function is going to do is to send the stop condition. So to send the stop condition, I write to this register. Then I can copy this code basically. And just replace register I check, stop. looks good. So once I've sent the stop condition, then I can wait for the last byte. I should also check the result here. Oh. And if I waited for if I received the last byte successfully, I will set the last byte inside the array I'm returning. It should be RX here, of course. So here I think we have something. Let's build. Yeah, it built. This is all there is for the I2C driver in this project. Since it's only, as I said before, I'm just going to poll, so I don't need to configure any interrupts or anything like that, which makes the driver a bit more simple. So what I'm going to do now is just to test to see that it actually works. And for that, I'm going to write a small test function called static void test I2C. And to test I2C, I obviously need to connect something to the I2C bus. And I thought it would be appropriate to use the same range sensor as I have on the robot for this. And I'm going to, of course, test it on the launch pad because I'm still using the development board or the launch pad in this video series for verifying all of the drivers. So let's begin by doing test setup, init, and then I2C init. This also means I need to include I2C here. So for a test purpose, I'm just going to read out one of the registers of the range sensor, and I think the most appropriate one to read is the register that contains the product ID, because that contains a fixed number that I can check against, and that's an 8-bit register with an 8-bit address. And the address is this one here, which you can find in the datasheet of this range sensor. And if I get an error, I'm going to print that I got an error. Otherwise, I'm going to check if I got the expected ID, and then I can print that I did. And if not, I can print that I read the unexpected ID. And one thing I also need to do before trying to read the sensor in this case is I need to make sure that it's not in standby, and to make that work I have to set I need to pull one of the pins high, a pin called the X-shoot pin, and that is just one of the pins that I'm going to be connecting to the range sensor. So that's just going to be a pin that I need to write to here. That's just specific to this particular I2C sensor. Once again, for details about this particular range sensor, I have a blog post which I will link to in the description. I should also set the slave address I'm writing to here, even though the default address is going to work in this case. Let's just set it here also. And the default address to this range sensor is 29 in hex. I can also wait for some time here to make sure that the sensor leaves standby, so you just wait 100 milliseconds maybe. And I'm going to add a comment here as well, just to explain what I'm doing here, since this test requires this exact type of sensor, this range sensor, to be connected. And before I run the test, I'm also going to connect my logic analyzer here, so that we can see the I2C traffic sent on the I2C bus. And I think it's really important, if you're working with any of the common interfaces, for example SPI, I2C, UART or anything like that, to also have a logic analyzer, because this allows you to get a better understanding or see what's going on the communication lines. It's especially useful during debugging when something doesn't work or when you're writing a new driver. So let me just hook this up now. And by the way, in my case, I'm using a more professional grade logic analyzer, which is a bit more expensive. But you can also get similar functionality from a cheaper logic analyzer, something like this. So this is what my setup looks like. I have my logic analyzer here, and then I have the range sensor here, and it has 6 pins. So 1 for power, 1 for ground, 2 for I2C, so the data and the clock line, and then 1 pin for interrupt, which I'm going to use to know when the range measurement is done in the actual range sensor driver. And finally the X-shoot pin, which can be used to set this sensor in standby. And similarly, I've connected them to the corresponding pins on my microcontroller. And one detail to be aware of when working with I2C is that I2C lines requires pull-ups. So I have 2 pull-up resistors here, and these are rated at 4.7k ohms, I think. And these are just necessary to make the I2C communication work. And for the logic analyzer, I have 1 connected to ground, and then 2 of the channels connected to either I2C line, so clock and data, which is going to allow me to inspect the traffic sent over the lines. So let's now try to run the test code. So let's build this example now. Test I2C. Oh, typo. Another typo. Oh yeah, then I also need to fix this pin here. It's going to be on I24. And inside, it should remove unused there as well. And then move this up to here. And I should have 3 here, I think, because I have unused 2, 3, 9, 11, 13. Yeah, that is. So now if we build this, yes, and then we can flash, open the terminal. It's not working. Let me investigate why. Okay, so I found a few mistakes I've made in my code. The main one is that I forgot to configure or move these to here, so that they're also configured for the launchpad, because now the pins was not configured for I2C, which means I hit an assertion inside here when I check the IO configuration. And the second problem is that made me not realize I got an assertion is that inside the UART driver right now, I might get stuck in this function here, since I'm waiting before I actually transmit the character. And this function is only used in assertion, and this is why I didn't notice it before. So I have to move this down here so that I wait after I send transmit the character. And then another issue that wasn't really a problem is inside the assert function, or inside the assert handler here. This should be 2 now, since I moved the left PWM signals to this pin instead on the launchpad. So now if I build and flash this, well, I should also fix another thing inside my test. I should add a busy wait here so that it doesn't go so fast. So now if you build this, and then if I, so this means that we get to here. So this means that we successfully read the value from this register, and we got the value that we expected. So let's also look at the traffic with the logic analyzer. And for this I'm going to use the software that comes with this logic analyzer from the same company, Saliae. And in my case, I have channel 1 connect the clock signal. So let me just, I can also just skip the analog channels and just have this. That's gonna be I2C clock. And then I don't actually have 0, but instead I have 2. And this is going to be I2C data. Then I can also turn on I2C for this and select data and SL, save. So now, okay, so now you can see, I can also see the traffic. So let's just pause this and zoom into one of them. So first here I send the start condition, and then I set up to write the slave address, which is this value here. And this is followed by an ACK from the slave. And then I write the register address, C0, which is also ACKed. And since this is a read transfer, I'm then going to reconfigure the I2C peripheral to act as a receiver, which means I'll send a new start condition, and then I set up to read, and then I send the slave address again, and I get an acknowledgement. And finally, I get the read value from the slave followed by an ACK, which signals that the slave doesn't have any more bytes to send. And finally, I send the stop condition. So up here is the clock signal, and here is the data. So as is visible here, it's very useful to have a logic analyzer when you are dealing with a communication protocol like I2C. Let's now also extend this test function to test the write function. And for this, I'm just going to write to one of the registers that I can write to on this range sensor. And I'm just going to write the value AB, and then read the value back to see that it has been written. I'm going to write to this register, the first register, trace the error if I get an error. Then I'm going to read the value back, and replace read. And if the read value is the same as the written value, it means it works. And if not, then something is wrong. So let's build and flash this as well. Okay. Oh, it shouldn't be a pointer. Yeah, and that works as well. So let's look at the traffic again. Zoom out a bit. Okay, so yeah, so this is the where we set up to write the slave address, and then we write the address to the register, and we write this value to this register. And shit. And then we are done with writing the value, send a stop condition, and then we start the transfer to read the value back from this same register. So here we reconfigure to read the value, and then we get the expected value back, and then we're done with this read operation. So everything seems to be working with the I2C driver. So let's now commit this driver, or let's just run a CVP check first. So get some complaints. Oh yeah, I missed adding the decrement here. That's not good. Oh, now it works. So let's just also see that it actually works. Yes, format. Let's just build everything. And commit. And push it. And check CI to make sure that it builds. Yeah, all checks passed. Good. This means that we are done with the I2C part of this video. So now we are done with this part. So then I can move on to the layer above, the actual driver for the range sensor. And as I said before, I'm not going to spend the time writing this driver from scratch in this video because it requires quite a lot of code and it would be a very long video and a bit tedious as well. So I'm just quickly going to show you the blog post that I made. It's right here. So on this blog post I go over in detail how this sensor works and how I create a driver for it. So yeah, quite a long blog post. So if you want the details about that, just head over to this page. But for this video, I'm just going to add it and copy in the code. Just like touch. So here is the interface for this driver. And there's going to be one function to initialize it. And then I will have one function to read a single sensor. And then I also have a second function to read multiple range sensors at the same time. And yeah, I add a comment here to explain exactly what these functions do. And then here is the implementation for this. So as you can see, there is a lot of code here. It's almost 1,000 lines. Quite ridiculous actually. I'm not going to get into the details of this. But note, if you read the blog post and check the associated code, there will be some differences compared to the code I have written here because I made some improvements this time around. But overall it works the same way. Okay, so let's add this to the makefile as well. And I also need to update the pin configuration here. I'm going to move this up here, and I'm going to remove the internal resistor here because I forgot that on the range sensors that I'm using there is already a pull-up resistor available on the breakout board, so I don't need the internal pull-up. This, and going to use this pin so we can remove 9 there. Check to see that it builds. Yes. So then I'm also going to add a test function to verify that it works. I also had to include the driver, so that's going to be drivers. And then in this while loop I'm just going to get a single range measurement in each iteration. Then I'm going to print the detected range. And for the launch pad I only have the front range sensor connected, so I'm going to retrieve the value. First of all, if it failed, I'm going to otherwise check if the range is a valid value, because if there is no obstacle detected in front of the range sensor, I'm going to I return out of range. And from this sensor I get the values in millimeters, and if it's out of range I'm just going to print that it is, and a small delay in between. So let's see if this builds. Does not. Oh, I missed this one. Can flash this. So now I'm not holding anything in front of the sensor, so I'm getting out of range. But if I move my hand above the sensor, I get the reading. If I have it a bit further away, closer, very close, Yeah, so that's working. And just for fun, we can have a look at the readings again with the logic analyzer. So in each iteration there is a bunch of traffic going to the range sensor, and I'm not going to go through them all, but this is just basically a bunch of register reads and writes. Yeah, and then I'm also going to create a second test function to test the other function where I read multiple sensors, but in this case I'm just going to read a single sensor still, so I will not be able to test this function fully until I have the actual robot, but I'm going to implement it now anyways. So again, I'm going to initialize, but here I'm going to use the other function. Since I have 5 range sensors, this function takes this array here containing 5 values and writes the readings to this array. And then I have a second variable that I pass to the function called fresh value, and this marks whether the values returned have just been sampled or not. Because for this function I'm not going to start a new range measurement each time the function is called. Instead I'm going to retrieve the last values read, and sometimes when I call this function there is going to be an ongoing measurement, and then I'm just going to read the latest value. But other times I may call it and there may be new values ready, and then I'm going to read those values from the range sensors. And this is just the way I decided to implement it for this application, since the overall code on the sumobot is going to run in a while loop, so I will be calling this function over and over again, so implementing it like this makes sense for this use case. But once again, exactly how this works, I explained that in my blog post. Then I print all of the values, then I can end with a busy wait here as well. So let's build this as well to see that it works. Oh, it does not work because I also realized while preparing for this video that I made another bug, and that is inside the IO driver where I set the interrupt flank. So these here should be the other way around. So now when I try to set it rising, it actually set it falling, and vice versa. So I have to just reorder these, but fortunately there is only one place where I set this trigger so far, and that is in the IO remote. So I just have to make sure that I switch this to like that. So now if I build this again, it should work. Yeah, and it does. So if I hold my hand over now, I get readings on the front sensor. Of course, I get the value 8190 on all of the other sensors, because that means they are out of range. And yes, that's just the default value I use now when they are not connected. So this works as expected. So let's move on to commit this code. So first, format, CPP check, git status, git add, commit. Also, I should probably have put the bug fix in a separate commit, but well, let's just put it in the same commit. So let's push this. See that it passes CI. Oh, I forgot to build everything. Let's just do that in the meantime then. So that passed as well. So this means that I'm done with this portion of the code as well. So I'm done with all of the driver code necessary for the enemy detection. So let's now finally add the small software abstraction layer here that turns the measurements into discrete enemy positions, which is going to be here to make the interface nicer for the rest of the application code. So in this case, I don't need to create any new files because I've already added the enemy files previously in a previous video, but I'm adding a comment on top of here. Then I will add an enum for the enemy positions. So there's going to be a bunch of positions that the enemy can be in depending on which range sensors are detecting something. So if nothing is detected, the enemy is nowhere, or we don't know where it is. If the front left sensor detects it, yeah, and so on. And then just for debugging purposes, in case I have some issue where the left and right sensors detect something at the same time for whatever reason, then I will just return position impossible, because it's not really possible for the left and right sensor to detect the enemy, because there is only supposed to be another enemy on the platform, and it cannot be on both sides at the same time. But for debugging purposes, as I said, it might be good to be able to return this. And I'm going to have a similar enum for the range to the enemy. So instead of giving the exact distance to the enemy in millimeters, I'm just going to return 3 discrete values. Either the enemy is close, or it's far away, or somewhere in between. So these 3 values. And then I'm going to group these 2 enums into a struct which I'm just calling enemy. So position and range. And then I will have a function that returns this. So it's going to be enemy get this. And then I will just add a bunch of additional helper functions which will make the application code more readable later on. These functions will just take the struct return from this function and, well, check if the enemy is detected, if it's at the left, right, or in the front, basically. And finally, I will have 2 functions to turn these enums into strings, which will make it a bit nicer when I trace them to the terminal. Of course, these are going to take up some flash space, so if I see that I run out of flash space later, I might actually remove these functions later on. But for now, I will keep them as is. So this is it for the interface. Let's now move into the implementation file. I also need bool here. This is just going to initialize the range sensor driver, which means I also have to include it here. Let me get the result here. And if I get an error, I will return, but I will also print something here. So let's now implement enemy get function. Create an enemy struct and give this some default values. And then I'm going to use the function for measuring multiple sensors at the same time. Maybe we should print something here as well. I don't actually want to spread too many traces since it takes quite a lot of flash space, but let's add this one anyway. And then let's extract the ranges for each sensor from the returned array and do this for all of them. And then I will have a maximum threshold to decide whether the enemy has been detected or not. So these are going to be bools, and I'm going to define this threshold to be 600, because even though the sensors can measure longer than that, they should never go above that, given that the platform is around 80 centimeters in diameter. And then I will have a variable to hold the range temporarily. I'm just going to go through all of the possible cases here. So first, this case, front left. If I detect left and front left, or left and right, that means I have detected an impossible range. Else, I'm just going to set left here and also set the range. Else, if right, there should be front right here. Front left or left. It's going to be impossible. Otherwise, But I'm actually not going to be using the values from the sensor on left or right, because when I used this robot a while back, I realized that I haven't actually mounted this in a proper way, which means that I will get a lot of false readings. So what I decided to do in the end was to simply discard the sensors on the side and only use the sensors in the front. But I'm still going to leave the code here, but I'm going to undefine it and add a comment about it. So let's move on to the sensors that I'm actually going to be using, the sensors in the front. So if all of them detect something, it means that the enemy is right in front of the robot. So then I should return position enemy push front all. And in this case, I'm going to average the range readings, which I can do by adding the first two values, dividing them by 2, and adding this value to the third value and dividing that by 2. Otherwise, if I detect front left and front right, that should not be possible. Then I'm going to set enemy position, enemy push bow. Otherwise, if front left and if front, it means enemy push front and front left. And then I'm also going to average the range. Else it is going to be push front left and range front left. And then I will do the same for front right, like so. And then I will check it's just the front sensor detecting it. Front and range front. And finally, if no sensors are detecting anything, it's going to be enemy position none. There should be range here. And if I didn't get the proper range reading, I'm just going to return enemy here. Otherwise, I'm going to convert the range into an enum value. And then once I've done that, then I can return enemy finally. So that's it for enemy get. And then for the other helper functions, this will just be one-liners. So first I have the enemy detected. So this just checks if the position is valid, because that means an enemy has been detected. And then the second function to see if an enemy is at the left, I will just check all if the position is a left position. And then I do the same thing for enemy at the right, check if any of the positions are right positions. And finally for enemy at the front, I check if any of the positions are a front position. And then I'm also going to add the string functions. So first this function, which takes the enemy position enum and turns it into a string for each enum value, so that I can print them nicely to the terminal. I also add a comment here saying that these string functions are just nice to haves, and if I run out of flash space, I should consider removing them. And then a second function that does the same thing but for the other enum. So let's see if this builds now. Yes, I need to add some additional defines. And for range close, I thought it made sense to put this at 100 millimeters, so 10 centimeters. So if the enemy is closer than that, it means I'm going to say that it's close to the robot. And mid is set as 200, and then far as 300. Oh yeah, these must of course be 16-bit integers. Now it builds. So let's finally create a test function for these two. Same as usual, set up the test, initialize tracing, and this time initialize enemy. And then in a while loop, retrieve enemy. The values using the string function, enemy push string, enemy position, and enemy range string, enemy range, and then a busy wait. Something like this should do it. And then I also need to include enemy. So you can see if this builds. Yes, and then we can flash it. So now I don't have my hand over the sensor, so it doesn't detect anything. But if I hold my hand over it, I get front mid. And then if I move it further away, I get front far. And if I move it closer, I get front close. So this part of the code also works. Good. This means I can format the code, run cpp check, edit, and commit. 23, and then push this as well. Again, I forgot to build. Yeah, and the final patch also passed CI, so let's rebase and merge this. Okay, so that was all for the code in this video, and now I think I finally finished up all of the code that I wanted to write using the development board. So because right now, just to sum up, what I've implemented so far is in the drivers layer, I've implemented the code necessary for initializing the microcontroller. I've written the driver for the IO pins or the IO configuration. I've also implemented a UART driver and software layers on top here to handle tracing and formatting strings. And in this video I implemented the I2C driver and added the driver for the range sensor, as well as implemented the small software abstraction called enemy. And then I've also implemented a driver for ADC along with a small abstraction layer for the line sensors called QRE1113, and then similarly a small abstraction layer inside for the application code here to provide a nicer interface to these sensors. And I've also implemented a driver for the IO remote, which is so that I can use a IO remote to control the robot, and this is also used for the for the start signal, or it's going to be used for the start signal later on. And then I've also implemented a PWM-based driver using the timer peripheral to provide a PWM signal to the motors, and and this is used by the motor driver to control the DC motors. And I've also implemented a interface on top here to provide a nicer interface for the rest of the application code to the motors. And I've also implemented a small LED driver to blink an LED. So what I have left next is this big application layer, basically. So what I'm going to do next, I think, is in the next video I will do the bring up of this sumo robot, because overall during these last couple of videos I have written the code in a way as to prepare for running it on this sumo robot. So ideally I should just be able to change the target I'm building for and flash it onto this robot, and it's going to work. But I've probably missed a lot of things, so that's something I will go into in the next video, where I'm also going to talk a bit about board bring up in general, I think. And once I have this robot working with the existing code, then it's time for me to start writing the application code, or the overall algorithm that this robot is going to be using to detect the enemy and push it out of the ring, and also avoid driving out of the platform. And for this I'm going to do some simulations and stuff. But this was everything for this video, so thanks for watching and see you in the next one.